Hello, my name is Alicia Park, and today I'll be presenting my honey descent in water experiment. In this demonstration, I explored the transition from laminar to turbulent flow using a simple yet effective setup in fluid mechanics. The core question driving this project was, what are the observable characteristics of the transition from laminar to turbulent flow during the descent of honey in water? This question allowed me to directly visualize a flow regime transition in a household setting, making fluid dynamics more tangible. Understanding fluid flow transitions is essential in many engineering applications, from chemical mixing and heat exchangers to materials processing and transfer systems. For this experiment, I chose the Reynolds number as my main model, and here's why. Reynolds number is one of the most important dimensionless values in fluid mechanics. It tells us whether a fluid flow will be laminar, transitional, or turbulent based on the balance of forces acting within it. The equation is RT equals PVL over mu, which basically compares inertial forces, how much the fluid wants to keep moving, to viscous forces, or how much the fluid resists that motion. So when RE is very low, like in this case for my experiment using honey, the viscous forces dominate and you get smooth, orderly flow, laminar flow. As RE increases, inertia takes over and flow gets more chaotic and unpredictable. The experiment was performed using the following materials: a transparent drinking glass filled with approximately 150 milliliters of room temperature water, 1 teaspoon about 5 milliliters of honey, and a smartphone camera to record the experiment. Before I started the experiment, I had to make a few assumptions to simplify the analysis. First, I assumed that the room temperature stayed constant at around 20 degrees, since viscosity can vary a lot with temperature. I also treated the honey as a Newtonian fluid, meaning its viscosity stays the same no matter how fast it's moving. Also, for the descent, I assumed it was perfectly vertical and there wasn't any friction from the glass walls affecting how the honey flowed. I used literature values for the viscosity and density of honey instead of measuring them myself, which is a common practice for these kinds of demos. And finally, I assumed there were no significant air bubbles and that the honey was released in a smooth uniform at the start. Also, I made sure to define the boundary and initial conditions clearly. At the moment I released the honey, I assumed the initial velocity was zero, basically it started from rest. The boundary was the water column inside the glass I used, which helped contain the fluid and define the space the honey was moving through. I also assumed a non-slip condition at the walls of the glass, meaning the fluid right next to the glass wasn't moving relative to it, which is a pretty standard assumption in fluid mechanics. Also, I kept everything at room temperature around 20 degrees and I tried to maintain an isothermal condition throughout the experiment. And finally, I introduced the honey as smoothly as I could without stirring or shaking the glass so the flow wouldn't be disturbed right from the start. Here some key measurements are recorded. First, I recorded the time for honey to reach the container bottom. Also, I measured honey stream width at 1 centimeter intervals. Also, I recorded the visual documentation of flow patterns. To set up the experiment, I filled a transparent glass with 150 To set up the experiment, I filled a transparent glass with 150 milliliters of water. Then I let the water settle to avoid initial turbulence. Then I gently introduced the honey at the top of the surface using a teaspoon, recording the descent using my smartphone. This slide introduces the theoretical foundation for my experiment, the Reynolds number. The Reynolds number helps us predict whether a fluid flow will be laminar or turbulent. The equation is RE equals PVL divided by mu, where P is the fluid density of honey, about 1.45 kilograms per liter at 20 degrees, V is the descent velocity, which I measured as 0.0125 meters per second based on honey falling 10 centimeters in 8 seconds. L is the characteristic length. In this case, for honey, it refers to the diameter of the honey stream as it moves through the water. I measured it to be around 5 millimeters or 0.005 meters. This value represents the scale at which the honey interacts with the surrounding fluid, influencing the flow regime. And for last, mu is the dynamic viscosity of honey, approximately 10 Pascal seconds at room temperature. Here's a visual breakdown of how different flow regimes behave based on the Reynolds number. When RE is less than 2000, the flow is laminar. It moves smoothly, often with a parabolic or bullet-shaped profile. Between 2000 and 4000, the flow becomes transitional. You may start to see some disturbances or instability. Above 4K, the flow is considered turbulent with chaotic swirls and eddies. So here's where everything comes together. Plugging the values of fluid density of 1420 kilograms per meter cubic, velocity of 0.0125 meters second, and characteristic length of 0.01 meters divided by a viscosity of 10 pascals, we get a Reynolds number of just about 0.01775, and this is way below 2000, which confirms that we are firmly in the laminar flow regime, and that matched what we saw: slow, smooth descent with a parabolic shape, no turbulence or swirling. So overall, the experiment validated our theoretical prediction, and the Reynolds number proved to be a reliable model for analyzing flow behavior in this setup. While I was doing the experiment, there were a few sources of error I had to keep in mind. First, the viscosity of honey changes a lot with temperature. Even just a small shift in room or water temperature could have thrown off the flow behavior. Then there's the measurement side. Since I was timing the descent and measuring the stream width by hand, there's definitely some room for human error. Another thing is the glass container I used. If the honey got too close to the walls, it might have changed how it flowed or interacted with the water around it. Also, the way I released the honey wasn't always perfectly consistent. Sometimes it might have been slower, faster, depending on how steady my hand was. And lastly, the video I took didn't always show the clearest detail, which made it a bit harder to confidently observe transitions or subtle changes in flow. Here are my references, and thank you for listening.